Okay, so we're recording now. So today we're going to continue talking about the generalized linear models. So just as a brief overview, on previous sessions we were talking about general regressions. So in the general case, we are interested in describing one variable in terms of another set of variables, right? So that's the main idea for a regression. So we might have n independent variables. We have a single dependent variable and we want a description. Particularly, we want to model the conditional probability of our expected of our target variable given the information that we can extract from the independent variables. In essence, we want to actually model the expected value, right? So in the case of the most common linear regression, so when we're talking about using the normal distribution as part of the linear regression, then we are trying to model the mean as a function of the independent variables. Now, in the previous session, we were talking about how to generalize this process. So we still want to have a target variable and a set of independent variables, but we don't want to be constrained on the probability distribution that we are using. So we want a more general approach. We want to be able to use different distributions according to um, different types of data that we might encounter, right? So for example, our overall goal is to create a regression model to estimate the probability of default. To incorporate the loan context, the request context of the loan, to incorporate that information into a better estimation of the probability of default. So that's the main objective. And we can take linear models to generalize over that approach. So far, we know the definition. We know that when we're working with a linear regression model, we are actually describing the expected value through a parameter of a distribution. Therefore, the actual distribution lives within that function, right? So the mean is going to be variable according to the independent variables, and we'll get a different estimations depending the different values of those variables. So that's what we know so far. Um, there are two key components. So we have the random element. So our target variable is a random variable, and therefore it has a distribution. And we are assuming the conditional distribution of y given x. And there's also the concept of the link function. So for the link function, if you remember on our previous session, um, we describe the value of the link function relative to the data that we want to work with. So in this example, we know that we are going to provide estimations for our target variable using a linear combination of the independent variables. So we're going to take a sample and we're going to provide an estimate, right? So for each observation, we can provide an estimate by actually doing the linear combination. Now, in this example, well, in general, whenever we provide the estimation, which is the matrix multiplication between the coefficients and the independent variables, then we have something like this, right? And since we do not control these values for the independent variable, then the result that we get by doing this sum is defined between minus infinity and infinity, right? So it can be any number of the real line. thinking of the individual case, so when we're talking about the probability of default, then we might incorporate in here the age, for example, in here the income, the annual income. So we do not control those variables. Therefore, the result is defined in a very broad domain. Now, this is fine for the normal distribution. So if we have our target variable, so if we have y in here, so if we have our, if y is part of the normal distribution, then the domain of y is defined in between minus infinity and infinity. Therefore, we don't have any problem by directly using the output of this linear combination to describe our target variable. So that's okay. But what if we have a different distribution? So for example, in the case of Bernoulli, we can only have values of 0 or 1. Therefore, we cannot go directly from the output of this linear combination to this domain. We need to apply a transformation. And that's the that's the main idea of this link function. So in essence, we use that link function to link the results of the linear combination to the results of our target variable. There are other examples. So if we are working with Poisson distribution, then we only have integer values. Therefore, we need to apply another function, right? So for the normal case, this link function is the identity. For the Bernoulli distribution, we're going to have a different function, a different link, and for each different distribution type, we're going to get different links as well. So that's the idea of the link, right? So we have a function that describes a parameter of our distribution, in this case the mean. So we have mu, that is a function of x, and if we apply the link function g, we should be able to directly represent that as the linear combination of the independent variables. So that's the main idea. Now we already know that we're generalizing over the distributions. We have normal distribution, exponential, we have Bernoulli distribution, Poisson distribution. Each of these distributions allows us to describe different types of data, right? So for the Bernoulli distribution, we're going to be primarily interested on binary events. So for example, the default scenario. For the Poisson distribution, we are interested on events represented by integer values, most likely frequencies, absolute frequencies. So for example, the number of loan defaults that we're going to have in a client portfolio. So depending on the nature of the problem and the types of the data that we're working with, then we can select different distributions. And we want to solve those problems with a regression. So representing the target variable with a set of independent variables. And the linear component is just making that representation, so the function that allows us to represent the key parameter of the distribution is going to be a linear combination of those variables. So that's the key component, right, on the generalization. So we want to get the conditional probability y given x, and we are going to allow that distribution to be any member of the exponential family. And therefore, we also need to propose a link function to make comparable, once we have our model, the output of the linear combination with the domain of the target, with the domain of the parameter corresponding to the distribution of our target variable, right? So that's the main objective. In the previous session, we started talking about the exponential family distribution. So we know the general form. We know that we have that this family actually contains plenty of very popular distributions. So here we have Bernoulli, we have Poisson, exponential, we have the Pareto distribution as well. So this is a very broad family that we can use it to solve very varied problems, right? And that's why these models are very used in the insurance industry because of the flexibility. So we can describe a lot of different types of problems using these models. Okay, so this is the general form. And we have a simplified form. So this is the canonical representation of the exponential family distribution. So by canonical, we mean that we only have one parameter. So let's think about the normal distribution. So the most common parameters on the normal distribution are mu and sigma, so the mean and variance. The canonical representation of this function only allows for one parameter. Therefore, for the normal case, we're only going to take the mean, in this case mu. There are some distributions that only contain one parameter. So for example, Bernoulli only has the probability for the event. Therefore, it only has one parameter. So we're going to take that, right? So these are the four elements of the canonical exponential family distribution. These are the four constraints. So we only have one canonical parameter. Our target variable is only defined on one dimension. And the two functions that operate on the parameter of the distribution and on our target variable are going to be the identity functions. So we are going to be working directly with the parameter and the target variable. As a result, we have this simplified version of the canonical distribution, where we have the multiplication of our target variable with the parameter of the distribution minus a function that only depends on the parameter of the distribution, a constant, and another function that is added just for flexibility, right? So this function only depends on our target variable and optionally on the constant. So this function is actually not dependent on the parameter of the distribution, and that's a key distinction. Okay, so we can do the same type of proof as before. We can structurally manipulate the distribution in order to match the structure of the canonical form, and then we can start replacing the different elements. So before moving on into this part, which we already also worked a little bit on the previous session, let's remember the case for the Bernoulli distribution. So we know that the general form for the canonical exponential family is like this. So we have the interaction of our target variable and the parameter of the distribution minus a function b. And we have a constant phi, and we have another function called c that depends on our target and on the constant, right? Okay, so what's the form for the binomial distribution? Sorry, the Bernoulli. So let's think about the problem. So we have an event. That can be either 0 or 1. That's actually our target variable. So this is actually our target. So in our examples, this is default or not default, right? For credit risk modeling. And we have a probability of occurrence. That is P, right? So by using this information, we can try to build the probability distribution function, right? So for our target variable y, we want a function that actually provides the probability of all the possible values that we can encounter. In this case, these are just 0 or 1. So how can we design this function? Well, we have the probability p. Y is only 0 or 1. Therefore, whenever we have the positive event, y is going to be equal to 1, and we're going to get our probability. So if the probability of getting 1 is going to be equal to p. What do we want for the probability of 0? So we want the complement, right? So 1 minus p. So if y is equal to 0, then this term will be cancelled. Well, it will be equal to 1, right? Which is not what we want, but we can work with that definition. So we can multiply this by 1 minus p. So we're close enough. When y equals 0, then this will be equal to 1, and we get the complement. But now when y equals 1, we don't get the probability as isolated as we would want to. Therefore, we can apply the same trick. And since this is basically a switch, right, that we can use the exponential to enable or disable the different terms. So in this case, the fix that we can provide in here is just elevating to 1 minus y, right? So whenever y is equal to 1, then this will be equal to 0. Therefore, everything in here will be equal to 1, and this part will be equal to p. Right? So this is correct. And when y is equal to 0, this part will be equal to 1. This will be equal to 1 as well, and therefore this part will be equal to 1 minus p, and that's the only thing that will survive from the whole equation. So we get our two scenarios. Right? Okay, so that's the the probability function for our target variable. Okay, so in the previous session we worked with that definition, and we arrive at the following. So we want to rewrite this form in the general form. Oh, sorry, here we are missing something. We were missing the exponential. So if we want to rewrite this in the general form, then we have the interaction of our target variable times this other component minus this component, right? So you can verify your notes on how to go from here to here. And well, we can start assigning the different elements. So for this case, well, we can actually propose our parameter to be this part in here, and this function will be this other part, right? Okay, so from here we can solve for the probability, so for p. And the solution, if you remember on our previous session, and you can verify the math later, so the solution for this case was p equal to this part, which we can rewrite as the sigmoid function. Great. So once we solve for p, then we can replace p in this other equation um, to actually have a function in terms of the parameters of our distribution. Okay, so we need to replace with p, and well, you can verify the math again later, but we got as a result. Okay, so that's for the Bernoulli distribution. And let's remember here we are working on two different levels. So for the first general level, we are working with the the general expression, but we are also interested on working with the particular case for the Bernoulli distribution. So you want a general framework or methodology to enable the path for us to use the Bernoulli distribution, but that will also enable um, that approach will also enable us to use different distributions for our regression problems. Okay, so we have here we have the solution for p, here we have the solution for our b function. Okay, so in the previous session we also worked with some properties. So here we took the expected value of the first partial derivative of the natural logarithm of our distribution, and we know that this will be equal to 0. And we also did the expected value of the second derivative, and we got this property. So what can we do with this? So in fact, we're interested in calculating the expected value of our target variable. So we want to know what's expected value of this variable. Now, we know that this variable has this distribution, right? And this is the general form for the distribution. So we can apply the property that we already know. So we know that the expected value of the first derivative of the natural logarithm of our distribution is equal to 0. That's what we already know. So let's actually derivate this function. So the first derivative, in here only y survives. Here we have the first derivative of b, and this relative to our parameter is equal to 0, right? So we have the solution, and then we need to apply the expected value over this part. So let's remember the expected value, the significant results on the expected value only occur for random variables. Our target variable is a random variable. Therefore, whenever we apply the expected value in here, we need to keep the expected value for y, and this part in here, since it's constant, we can just leave it as it is, right? So the expected value of a constant is the exact same constant. Now by solving for the expected value, we get that the expected value of y is equal to the first derivative of our function b. Why is this relevant? Well, because we can actually identify what's that function b for any of the functions defined for the on the general exponential family, right? So if we can make the particular distribution in this form, we can identify what's this function, right? And if we apply the first derivative, so let's do it in two different ways, right? So if y is part of the Bernoulli distribution, what's the expected value of y? So the expected value of the Bernoulli distribution, it's the probability of the positive event, which is p. So we know this statistically. Now, what the math tells us is that if we take the first derivative of b, we're going to get the expected value of y according to this part, right? So let's see if this holds true. So let's take the derivative of this part in here. So here we have a compound function. So we need to do the chain rule, right? So we need to apply the derivative of the outer function times the derivative of the inner function. So the derivative of the logarithm is 1 over x. So in this case, 1 over x, and x is 1 plus e to our parameter, times the derivative of the inner function, which is the derivative of e to the x is equal to e to the x. Therefore, we have this, right? And we already know that this is equal to p. So it makes sense, right? So everything we know so far makes sense. And we can get the expected value now only by knowing the function b. Same for the variance, we only need to apply the second derivative, replace everything, solve for the variance, and we get now that we can also describe the variance by this function b, by the second derivative of this function b. This is a strong property of the canonical representation of the exponential family, because for any member we can get the the expected value and the variance only by knowing the first and second derivative of this function. Let's take as another example the Poisson distribution. So this is the general form for the Poisson distribution. We have one parameter mu, we have our target variable y, and this is the form, right? So in this case, it's very easy to refactor this formulation into the general form. We only need to apply the exponent, and for doing that, we only need to apply the logarithm on this part, right? So we have the result in here. Okay, so the different elements, we have our target variable multiplying our the definition of the parameter of the distribution. Therefore, we do this assignment. We have a function that depends on the parameter of the distribution, this part in here, and we have the other complement of the c function that only depends on y or on the on phi, which is the distribution, sorry, the dispersion constant. In this case, phi is equal to 1, right? So this is going to be equal to c. Now here we have a very similar case to the one that we got in here, because we have b in terms of p and not in terms of the parameter. We have the same in here, so we have b in terms of mu instead of this other parameter, but we can easily replace this part, right? So we know that mu is equal to e to the power of our parameter. So this part, so we got this part, right? So now if we apply the first and second derivative, we have the mean and the variance, which is consistent with the definition of the Poisson distribution. So for the Poisson distribution, the mean is going to be equal to mu, and also the variance. And it is equal to mu because of this quantity, right? So this makes sense as well. So now let's talk about the link function. That's something that we have not yet solved. So let's remember, the link function will be useful in order to make compatible the output of the linear combination with the domain of our target variable. So that's the key function of this link, right? It's part of the definition for the generalized linear models. So far we have been talking about the exponential family distributions and two different cases. So the general form and the canonical expression. And we identify some key properties like this. Once we identify the b function, we can get the expected value, and we can also get the variance. So now let's go back to our model definition. So our main objective is, let's take whatever member of the exponential family distribution, right? And let's try to get a compound distribution, so y given x. And we're going to try to model one parameter of this family, of the particular distribution that we're working with. We're going to try to model one parameter as a function of x being all the independent variables that we're going to incorporate into our model. So that's our main objective, and we need to introduce this concept of a link function because of compatibility of the different domains, right? Now, what we want for this link function, so it's easier to think about in terms of a transformation f. So if we have a function that describes our mean or the parameter of the distribution, right? This function, we can represent it as a transformation over the result of the linear combination of the independent variables. Right? In this example, if this outputs a number from minus infinity and infinity, then we can apply, let me do it in a different color here. Give me a second. So we can go from that definition into 0 or 1 by applying f, or we can go from 0 or 1 into minus infinity or and infinity by applying g, right? And f is the inverse of g, and vice versa, the inverse of f is g. Right? So we need to enable to define this function, and this is not part of the training of the, this does not interferes with the linear element of our linear model, because we're keeping a linear transformation to estimate the expected value for our target variable, and we are incorporating an additional transformation in between, right? Right, so the function that describes the parameter of our distribution is going to be a transformation f applied over the combination of the independent variables. In other words, if we apply the inverse of f in both parts, we have the inverse of f over this function. We're going to call the inverse g, and that's what we're going to be working with. So g applied over this function will be equal directly to the linear combination of the independent variables, and that the nomenclature of g is actually very common in the literature, right? So that's why we're also using g in this class instead of f. Although f is a little bit more intuitive, g is the convention. Okay, so we need to think about g. What can we propose as this function? So there are some properties that we need to be sure that they apply. So for this function, we know it will serve as a mapping between the domain of y and the domain of the linear combination, and these are the three properties that must be satisfied by this function. And by definition, they are also satisfied. So the first one is that this function must be continuously differentiable. So this means that this is not a stepwise function. It's a single function that we're going to be using. This function is expected to be strictly increasing, right? And G will provide the mapping between A and R, where R is the real line, right? So we also know that due to the definition, right? So G applies over a domain A and gives us a domain R, which is the real line. Right? And by guaranteeing these three items, then we know that the inverse of G exists. And we also need that inverse to exist because we are actually representing a duality, right? So G and F, and F, the inverse of F is G. So we need that inverse to exist. Therefore, these are the conditions that should also be met. Okay. Okay, so what do we know so far? So far, we understand the canonical form, right, of the distribution. We know that for our modeling purposes, we want that the parameter of the distribution to be represented as a function of the independent variables. So that's mu of x. And we know that this mu of x, so the expected value of this function, is the first derivative of b. We also know by definition that by applying g over this function mu of x, we are going to get directly the linear combination. So we're getting closer to our objective. Let's remember, our objective is to propose a methodology to calculate the best possible values for the weights of our model. So the parameters of our model. Here we have two different sets of parameters. One is the parameter of the distribution, and the other ones are the parameters of the model. Those are different things. Parameters of the model are these weights, and the parameters of the distribution are the theta value that we're using here. Okay, so we know by definition that by applying g over the function that represents the expected value, we get directly this linear combination of the independent variables, and this is very important. So once we understand this, we can kind of see a path, right? So we know that by using the first derivative of b, which is this one here, we can go from our parameter theta to the function that describes the expected value, right? So we can go from this parameter to this function. And by using g, we can go from this function, which is in here, to the coefficients or parameters used in the linear combination, right? So we can now start linking all the different elements. We are still missing what to do with this function g. So far we can calculate mu by applying the first derivative over b, but we do not know what to do with g. Right? So there's this concept of the canonical link. So if we're using the canonical representation of the exponential family distribution, there's an associated canonical link, and it's defined as the following. So we already know this part, right? So we have the link g that allows us to link the expected value, so mu, with the parameter of the distribution. And we know this because of the definition, right? So the canonical link will allow us to map directly by applying the link, the parameter of the distribution. So this is part of the definition of the canonical link. In the general sense, the link is used to map, right, directly to the linear combination of the independent variables. In this case, we are proposing that the parameter of the distribution will be represented by this linear combination. So that's the canonical link, the definition. Now, we know that the expected value is the first derivative. And the expected value, we want that expected value to be a function of the independent variables, right? So the first derivative will be a function of those independent variables as well. And by knowing this, which is part of what we have developed so far, right? Then we can take this expression. So we already know g applied to mu of x is going to be equal to this value. And this value here, by definition, is equal, so if we take this and we apply the inverse of the derivative of b, right? So we apply the inverse of the derivative of b to mu of x, then we're going to get our parameter. So this part is equal to this part, and this part is exactly the same, right? So if we have this equality, then this means that g is equal to the inverse of the first derivative, or vice versa. The first derivative is equal to the inverse of g. So by using the canonical link that is defined as this part in here, then we get that we can actually use the inverse of this first derivative as a possible solution for the link function. So in the Bernoulli distribution, so we already have this, here we have the first derivative of b, which we know is equal to p, right? Which is equal to the sigmoid function. So by using the inverse of this first derivative, we can get the link function g. Right? Any questions on this part? Okay, so um, that's the usage for the canonical link. We actually now have a way to propose this value. So why are we interested on the inverse of g? Because f is the inverse of g, right? Therefore, we can take the linear combination of the independent variables, apply the inverse of g, and get mu of x, which is the expected value. That's why we're interested in the inverse of g. Okay, so what are the modeling implications on this? So we now know the full path for the general case and kind of the specific path for um, for the Bernoulli distribution. So what are the modeling implications? When we are talking about modeling, let's remember we want to actually identify what's best set of beta values or parameters for our model. So that's the training of the model. So let's see what we can do with what we know so far. Okay, so we have the conditional distribution y given x. We want to model the expected value of this conditional distribution. We know that we only have one canonical parameter, and we want this to be a function of x, of the independent variables. We can get this value from this part, right? So this is something that we already know. So the function that represents the expected value of y when we are talking about a canonical exponential family member is equal to the first partial derivative of the function b. Therefore, our parameter can be modeled by this part in here, which is exactly the same what we already have in here, right? So this parameter is equal to this expression, the same that we already have in here. We know that we can get mu of x from applying g over mu of x. So we have g over mu of x is equal to the linear combination. Therefore, if we apply the inverse of g in here, we should be able to replace mu of x with that value, which is what we have in here, right? So here we have mu of x, and we only replace mu of x by applying the inverse of g over the linear combination of the independent variables. So we have this part in here. Once we have it like this, we can actually do the function composition between these two functions and apply the inverse. So that's our final notation. We're going to do the composition of g and the first derivative of b, apply the inverse, and then use that function to get the on the result of the linear combination. What will give us this? Well, this will give us the parameter of the distribution, right? We can represent this part as another function h. So the parameter of the distribution is a function h over the linear combination of the independent variables. Now there's something interesting on this approach, because we know that if we use the canonical link, if we use this definition for the canonical link, we know that the inverse of g is equal to the first derivative of b. So here we have the first derivative of b. Therefore, if we were to use the canonical link, we should be able to replace this value by the inverse of g. And the composition between a function and its own inverse, it's equal to the identity, right? And the inverse of the identity, it's the identity itself. Again, that's the actual definition of an identity function. So if we in the modeling implications, if we assume that we're going to be using the canonical link, then the parameter of our distribution is going to be equal to the linear combination of the independent variables. And that's how we join together all the different pieces, right? Because we have this general form for our model, sorry, for the distribution. We have the parameter of this distribution, and here we are proposing that this parameter will be estimated directly by the linear combination of the independent variables, right? So by using G as a canonical link, H is the identity, and then we have a very powerful model, because only by knowing the function B, we can completely describe or characterize the distribution, any distribution from the exponential family. And we have linked everything from the definition of the distribution to the proposal of the link function using the canonical link, and all the way through the estimation of the parameter of that distribution by using directly the output of the model. And that's exactly what we want, right? So how can we use this information now to create a model, to actually find the best values for the weights of the model? So in this case for B, not for it, sorry, for beta, the parameters. So for this case, we can propose a methodology. There are many different methodologies. You remember also the previous sessions when we were working with the linear model for the normal distribution. We identified 3 different methods, which I don't find in here. Oh, yeah, so we have the analytical solution, we have the gradient descent, we have the linear algebra approach as well. So there are plenty of different methodologies. In this case, we need to propose an equivalent to the error function. But instead of an error, let's think about let's use a probabilistic approach. So since we're working with a distribution and we are estimating a parameter of a distribution, we can use the concept of the likelihood. So for example, let's say that we have our data set, right? And we are trying to describe y given a set of independent variables x, right? Now we know that y has a distribution, and we're going to use the values of x to estimate a parameter of that distribution. Therefore, we can evaluate the probability of getting these particular observations, so each line of our dataset. We can actually try to get the overall probability of getting that particular sample. And since for the linear combination, these beta parameters are actually variables, then we need to find the best values for these parameters that maximizes the probability of getting this particular sample. So that's how we fit the data to the model, right? So how the best values that we're going to get for our beta coefficients that makes this sample most likely to obtain. So that's why we're using the likelihood. In this case, as we said before, there are different ways on solving this problem, but one of the most common ways is to using the likelihood directly. So we want to maximize the likelihood. To make it easier, we can apply a logarithm over the likelihood, and since the logarithm is a monotonically increasing function, then the maximum will remain the same, right? We're interested on getting the max log likelihood. So we can define the likelihood like this, right? So the likelihood over our parameters for the model is defined as the summatory of all the samples that we have. So we have m samples in our data set, right? So we have m rows. So we have the summatory of the logarithm of our function. So just a quick comment here. Here we're using the summation because in order to get there are some assumptions that we are making, right? So we can calculate the probability of row 1, and then calculate the probability of row 2, and so on, right? But the overall probability is a multiplication or the multiplicatory of all the individual probabilities. And by applying the logarithm, we can change from the multiplication into the sum, right? So that's why we're applying the log likelihood as well. So we simplify the problem. Now the logarithm actually cancels out with the exponential in here, and we are left with this representation. And we can also replace, since we already know by the canonical link, we already know that the parameter of the distribution, we can replace it directly by the combination of the independent variables. So instead of using here the parameter, we can use directly the combination of these independent variables, right? So this is what we're going to be working with. Now, once we have the log likelihood given a data set, in fact, this is the part where we switch from probability. Everything that we have been looking at before is just probability, and now we will be working with statistics, right? Because we are now using a particular dataset. So we'll be working with the samples on our dataset to estimate the values of the coefficients of our model. And one approach, well, we can get the derivatives, right? Using as a variable our coefficients. So if we actually do the derivatives for this expression, then we can rewrite this as the following. So let's derive this part when we are left with x and y here, times, and here we have the chain rule as well, the derivative of the outer function times the derivative of the inner function. So we have this in here. We can factor out the x in this part and we get this final result. So okay, any questions on this part? Okay, so once we get these first derivatives, we should be able to work with this definition and propose an algorithm. But first, let's see how this looks back in our in our Bernoulli solution. So far we know this about Bernoulli. Give me a second to connect back the whiteboard. Okay, so from here we also know that our parameter of the distribution is going to be estimated by the linear combination of the independent variables. Okay. So let's apply the log likelihood here. So in the general case, the likelihood, we can represent it as the multiplicatory of each of the elements in our data sample. And we can apply our Bernoulli distribution approach. We know that by applying the logarithm over the log likelihood, and also by replacing this expression by the general form approach, this one here. Let me just copy over this part. Okay, here we're going to get now the summatory, the summation of these values in here. So this so far will be completely equivalent to this part in here. Right, so by replacing with these values in here, so we know that we can replace the value for the parameter of distribution. This part is this in here. This is our b function. Here we have y. So we can represent it directly like this. Now from this definition, we can start working on now replacing with this definition and with this other definition. Now if we apply the partial derivative of our log likelihood, okay, so in here we also need to apply the chain rule. And this, so we need to apply the chain rules 3 times, right? So one for this, another one for this other part, and the last one for this inner exponent. Therefore, we end up multiplying everything back again by x. And there's actually a consideration in here. So this partial derivative is actually relative to a particular coefficient, the same as the other problem that we were working with for the linear model. So if you remember, we have partial derivatives for each. So we have partial for beta 0 and beta 1, right? Therefore, this is for a particular value. And as a result, this one is also for a particular x. This will remain for um, as the standard matrix multiplication. Here we're only selecting one x because of the general case, right? So we have this. Okay, so relative to partial derivative, then everything will be equal to 0 with except of this term, right? So that's why this xi is the only one that survives on this part. Okay. Well, we actually can simplify everything in here. We have done that before. You remember this part, right? So we can actually rewrite that as a sigmoid. Okay, what else can we do in here? Oh, we were missing as well. Since we did the partial derivative in this term, the same, exactly the same part applies, right? So this x, it's actually just xi. And well, by doing that, we can actually now just have y minus the result of having the sigmoid in here times xi. So that's going to be our generic partial derivative. Now let's go back in here. So in theory, this will be the general form. Let me rewrite it in here. So what we should get according to the abstract solution is this part in here, and it makes sense, right? Because the first derivative of b is the sigmoid function applied over the linear combination of the independent variables. So we actually got exactly the same. But this part in here is um, specific for the Bernoulli distribution. This part in here is general, right? So if we have the value for b, the function b, we can actually um, do this same approach for any other distribution. Okay, so now that we have this representation for the partial derivative, then let's now work on on proposing a methodology so we can do the same approach as the gradient descent. But in this case, we want to maximize the log likelihood. So instead of going um, in the other direction from the gradient, we are going to follow the gradient. So instead of gradient descent, this will be a gradient ascent, right? So we are going to follow the gradient to get the maximum value instead of the minimum. There's actually different methodologies that we can incorporate in here. There's a very cool library from Google called JAX. I think we have already talked about this in another session. Yeah. So JAX has an implementation to automatically differentiate Python functions. So you can actually define any function and you can get the gradient or the derivatives for that function. The actual implementation is very interesting. But yeah, if you're interested, I can share some resources. But instead of using JAX, we're going to do it the old way. So we already know how to calculate the derivative. So this is the general approach. So we should be able to code a simple solution just to test if all of our math, all of the things that we have done so far, if they make sense. Okay, so let's work on a very simple algorithm. So we will be using the gradient ascent algorithm. Although there are some better algorithms that are capable to incorporate additional information and actually to converge to a solution in a faster way. Nonetheless, well, we can generalize directly with gradient, with the modification of the gradient descent. So let's use here an example, LM for Bernoulli distribution. So let's start with the common imports. Let's get our data. So I have this sample dataset. Okay. So let me rename the columns. These first two columns will be our independent variables, and this last column will be our target variable. Okay, so we have, this is our data. So let's take a look into our dataset. So let's plot with a scatter plot x1 and x2. Okay, so these are our data points. Let's add a color. So whenever we have 0, let's use a blue color, and 1, let's use a red color in here. Okay, so this is our data set, and we want to differentiate between the blue and the red dots. That will be our objective now. You notice why in this case? So y only has 0 or 1 values. So this is exactly our Bernoulli problem, right? So in traditional or in simple models, and actually the probability of getting 1, we can get the overall probability by doing this. Right? So the probability of getting 1 is 0.6. But we know that we should be able to better differentiate that probability by incorporating the information of x1 and x2. Right? So if we get that value, then we might probably have a better performance. Right? So that's the idea and the objective of any regression. Right? Incorporate information of external variables to describe our target variable. Okay, so let's see. So let's follow a very similar approach to our linear model using gradient descent. Oh, let me complete the title here. Okay, so the first thing in here was to create. So we have this concept of the error function. In here, let's create get. So instead of an error, we have a gain function. So let's create our get log likelihood. So remember, for the error function, we require knowing the parameters. So let's do exactly the same for this case. But instead of specifying particularly these two parameters, let's work with a generic approach. So we want to enable any number of parameters. Now, to facilitate working with these parameters, I will transform them into NumPy arrays. So here we have a list. Now in here we have an array, just to facilitate using the matrix multiplication. So as an inner function, I'm going to define the likelihood. Now let's remember, what do we need to calculate the log likelihood? Let's go back to the definition. So for the log likelihood, right, we need the summatory of all the samples of our data sets. Right? So we need our actual data set. So let's get our data set in here as an output, as an input, sorry. And what will we get as an output? Well, we get a single value, right? The result of this sum. So it's a float. How do we calculate that? Well, let's figure it out. And let's return this function. Okay, so we need to do the sum Of what? Well, of applying our distribution without the exponential. So for each observation, so we need to iterate for each row. Okay, so in here we need to apply this part. Let me switch. So we need to multiply. Okay, so we need to multiply these two values, the weights, with the x values, and then multiply by y. Okay, so let me first work on this multiplication. So each row in this case contains the x values and y. So we take the row and we drop y, then we are only left with x values, right? We can multiply the matrix multiplication with the weights. That will be either this or this one here. Now let's just multiply by y. Y is a scalar, right? And right after this multiplication, we have a scalar. So let's multiply by y minus the natural logarithm of 1 plus the exponential of that multiplication. Okay, let's see if this works. So by executing this part, we should get a function. And by providing our dataset, we should get a single value. Okay, works great. Now this we're going to be trying to maximize this function. Now the next thing is to get the partial derivatives. Now we already know how to get a generic partial derivative. So let's create now our function. Get partial derivative, partial beta, for in the position I, and let's also provide all the other parameters. Same as before, let's facilitate using the weights as an NumPy array. Now for this implementation, what do we need to get the partial derivative? Well, since it's the partial derivative of the log likelihood, we still need to do the summatory. So y minus the sigmoid function times x in the position I. So that's what we are going to be implementing. So it's the sum for each of the elements. And let's get in here. We're going to do here y minus the sigmoid times the x at the position I. So for to getting the x values, we can do this and index on I. Now here we get y minus the sigmoid, which is 1 over 1 plus the exponential of the negative result of the linear combination. So that will be this multiplication. Okay. Now let's see if this works. So if we provide the position and the two values, and then provide the data frame, oh right, so we need to provide here the data frame. Okay, it's working fine. Now the only thing left to implement is to actually the training, right, of our algorithm. So let's keep track of the log likelihood values. We need to be sure, same as we did with this example. So here we kept track of the error function values. So let's do the same for the likelihood, just to verify that we are actually maximizing. Let's initialize the weights. So let's do this len. Let's take our data columns, -1. So let's initialize this with zeros. Let's get our learning rate and the number of iterations. Now for each iteration, and let's follow the same template as in here, we need to actually calculate the partial derivative for beta 0 and beta 1 and update the values. But instead of doing it sequentially like this, we can actually just do it over a for loop, right? So let's create, update the model coefficients. So we can get our partial beta, which is just applying this value. We provide I and we provide the weights. And then we only need to update to evaluate this function over our dataset and update the corresponding weight in the position I. So we're going to take the value we had before plus. So instead of minus, we're using a plus. The learning rate times our function evaluated on the dataset. Okay, that should update these the weights Now let's just keep track of the likelihood values. So let's append. We need to call this function. Let's provide the weights and the data. Here we're missing a parenthesis, and now it's running. Once we get the results, well, let's start implementing that part. Let's get a data frame. Let's get the log likelihood values. So here we should expect, so instead of an elbow curve like this, we should expect an increasing behavior because we're maximizing the likelihood. Yes. Okay, great. We got our results. Let's see the weights. In theory, if we get our data and we do the linear combination of the independent variables, let's get the probability, right? So for this, we should be able to get x1, x2 values and our weights. Okay, this is not yet the probability. We need to apply the sigmoid function. Why the sigmoid function? Well, if you remember, by using the canonical link, we can actually, the first derivative of b is the inverse of g. And we know that the first derivative of b is the sigmoid function, and that is exactly a function that we need to apply, so the inverse of g, over the result of the combination of the linear combination of the independent variables to get our estimation of the expected value of the distribution. For Bernoulli case, the expected value of the distribution is the probability of default. Sorry, the probability of the positive event, for which we are going to be using the default scenario. So let's apply the sigmoid. Sigmoid, it's defined 1 over let me do a very quick landing here. And let's apply the sigmoid over these results. Okay, so this is actually the probability. So given x1 and x2, this is the probability of getting 1. Okay, so let me do this very quickly. Let's filter out only where y is equal to 0. Okay, yeah, so we have a very good distribution. Well, um, I will explain this part on a following session. Just to finalize this part, let me verify, since this session is also being recorded, um, for you to get this later on. Let's just verify very quickly if by training with another model, so directly a logistic regression, we're going to get the same weights. Here we have, you can install scikit-learn like this, and in here they have a logistic regression implementation. Here we want to create an instance, and we don't want to feed intercept. Okay, so for the feed method, we need to provide the x values which we have in data without y. And we need to provide the y values. And let's ask for the coefficients. Okay, so it looks like our model is working fine. Yeah, it's working exactly the same as the logistic regression for scikit-learn. So that's it, the implementation. The power of the generalized linear models is that we can actually do any kind of regression supported by a distribution that is member of the exponential family. And what we only need to do is to fix or to update this part, right? So this part in here. So once we know the b function and we get the partial derivative, we can use the first partial derivative to use as a link function, as we just did for the case of this sigmoidal. And we can also use that first partial derivative as to guide the gradient descent algorithm by using this formulation. So we can solve any possible regression problem using any possible distribution from the exponential family by following those steps. And of course, there are better ways to get the optimal beta parameters, but at least using gradient descent is a familiar and easy way of doing that particular implementation. Well, so that will be everything for today's session. Thanks everyone.